Well, thank you again. It's a real pleasure to be here, and enjoyed meeting the students and the faculty today. So I guess this is a fairly informal event, I presume, so please do not hesitate to stop me any time with any questions. Is my mic working? Oh, I haven't turned it off. Yes, okay. Is the mic working now? All right. All right, so I'm as Lorenzo said, I'm a condensed matter physicist who normally thinks about electrons in complicated materials and how the entanglement of the electrons can lead to interesting new phases of matter. So that's roughly what I want to talk about today, which is a phase of matter called the strange metal. Let me see if I know how to work this. There, that's the strange metal. And it's a topic that's been occupying me for more time than I care to admit. But what also I want to talk about is there's been a somewhat completely unexpected at some point, but slowly emerging and rapidly developing connection, strangely enough, between strange metals, which are phases of electrons in a little crystal in a lab, and a black hole, which is usually a massive astrophysical object. But there's a primitive version of a black hole, which turns out to have, as I hope to explain to you by the end of this talk, the same quantum theory as a strange metal. Okay. So hopefully that sounds completely insane, and I would have said it as insane if I had, I didn't even dream of such a thing, certainly when I was at Yale. But once I went to Harvard, I lost it. Okay, so what is a quasi-particle? So one important theme of my discussion will be a quasi-particle. And a quasi-particle is a very powerful tool that's used by condensed matter physicists for understanding the properties of real material. So, when you learn quantum mechanics, you learn about how to solve Schrödinger equation for one electron around a nucleus. And that scares a lot of people out of physics. I mean, it's a complicated thing to do. But what about when you have 10 to the 23 electrons, which are freely moving in a material like copper or aluminum? How do we apply quantum mechanics to understand the properties of aluminum? First of all, it turns out that quantum mechanics is essential. We can't understand why a metal conducts electricity or why a metal is shiny without knowing about quantum mechanics. It's totally crucial to the collective properties of these electrons. Now, the electrons, in addition to moving in the lattice, also repel each other. And so you have a very complicated problem of solving Schrödinger's equation for 10 to the 23 electrons. There's just no way even a quantum computer could do that. So how do we make progress? And incredible progress has been made over the last 50 years. And really the hero of the story is the quasi-particle. It turns out that, if you have an electron moving in some environment, so that's the real electron, in most metals, it basically looks like an electron too, with some dust around it. And so that object there is a quasi-particle, but it's got the same charge as an electron. It usually has a different mass from a single electron, has the same spin as an electron, and most importantly, it lives a long time. It just looks like a particle for quite a while before it eventually decays. But it lives long enough that you can basically treat it like almost a free electron. So rather magically, even though we start with a complicated interacting system, we end up at the end of the day in many, many materials with these quasi-electrons to work with. So for example, in a metal like copper, you have the electrons moving at some momentum k, and these are different energy eigenstates as a function of k. So at low temperatures, which is room temperature, you basically occupy all of the lowest energy states up to this point that's called the Fermi energy. And to create a quasi-particle, you excite some electrons from a filled state to an empty state. And so now we have this particular electron will start moving. And it's moving, it's going to collide with the other electrons here. But it turns out it collides rather weakly, and only just by dressing it a little bit, you can mostly ignore this sea of electrons. So you have this one quasi-particle here, a quasi-particle here, and this is a quasi-hole. So you also have positively charged carriers. And knowing about these positive and negative carriers in the electron gas is the crucial principle behind the entire electronics industry. Transistors and integrated circuits are all built about playing tricks with this gas of positive and negative carriers of electricity. So that's just one of the examples of the great success of the quasi-particle principle, but it's really not, by far, not the only one. Basically, if you open up a textbook even today of condensed matter physics, every chapter is using the quasi-particle idea without even saying that it's doing it, because it's so powerful and so prevalent that we don't even realize you're making such an assumption. But in fact, you are. And here's a list of various successes of condensed matter theory in understanding various different types of materials: metals, insulators, semiconductors, superconductors, metals of disorder, and so on. I just mentioned the very last one, which is called the fractional quantum Hall effect. This is a rather bizarre phase of electrons in the presence of very strong magnetic field, when electrons are constrained to move just in a single plane. Now, it turns out in this state, the quasi-particles exist, but they don't carry the charge of an electron. In the simplest case, they carry 1/3 of the charge of an electron. And these are quasi-particles called the Laughlin quasi-particle, because Laughlin first realized they existed and eventually got the Nobel Prize for that prediction. So in this state, they're not the same as the simple one electron, the metallic states I was talking about earlier. There is a quasi-particle, but it's not an electron. It's some other much more non-local object in terms of the original electron, but it's some excitation, some lump that still looks like a particle. It just has some bizarre quantum numbers. And a huge part of modern condensed matter physics is studying these bizarre types of states. Today we say that such states have topological order. These are topological materials, and that's another vast subject, condensed matter. Today, last year's Nobel Prize was given for some of the early work on topological matter. Okay, the subject of my talk will be the high temperature superconductors. So these are complicated materials, and here's an example of a crystal called yttrium barium copper oxide. It's a very complicated material, but I really won't go into any of the details. And as you change the density, the composition of these ions, which amounts to changing the density of electrons that are itinerant in this square lattice down here. So this is the density, this is the temperature. You get a whole bunch of complicated phases, one of which is the superconductor, which conducts electricity with zero resistance with a critical temperature that can be as high as 100 Kelvin. And that's why these are called high temperature superconductors, because before 1987, when this class of materials was discovered, the previous record was around 20 Kelvin or something. So it jumped up to 100 Kelvin, and which is above the boiling point of liquid nitrogen. So these are materials which you can easily do even on a tabletop or demonstration with some liquid nitrogen of superconductivity. All right, so these were discovered in 87, as I just mentioned, and since then, people like me have been busy trying to understand them. And we've run into many, many roadblocks. And one of the reasons for the roadblocks is that when you go above the critical temperature, and this is the main hero of my talk, you get this phase called the strange metal. Anyway, so I'll try to tell you a little bit about it by giving you some examples of its properties. But in the one word characterization is this turns out to be the kind of the textbook example of a metal or of any state of matter which doesn't have quasi-particles. Okay, so everything I mentioned so far, including these topological states, have some kind of the excitations above the lowest energy state are just little lumps that move in straight lines. Here it doesn't seem to be the case, and the reason for this, it seems pretty clear, is kind of quantum entanglement. So you've probably heard of the EPR paradox, where two electrons can entangle with each other with the up and down states, and if you separate them, they still maintain that entanglement. So that entanglement feature of quantum mechanics for two electrons also applies when you have millions and millions of electrons. And so we have to talk about the collective entanglement of these electrons. And the entanglement, again, just very roughly, in these states is complicated enough that it doesn't allow for any simple excitations. And I'll give you some picture of why that's the case. Anyway, this strange metal also has many other names, and they're rather pejorative. Some people call it strange, other people call it bad, other people, there are literally many, many papers on strange, bad, and incoherent metals. Sounds like we hate this particular phase of matter, but no, really, it's really extremely fascinating. We just don't realize we're insulting it every time we talk about it. And so what is strange about it and what's bad about it? Well, what's strange about it is simply that it has no quasi-particles. What's bad about it? Well, what's bad about it is the bad metal, meaning it actually has a very large resistance. So in 2 dimensions, if you take any conductor in 2 dimensions, the conductivity has the units of fundamental constants of nature. If we divide Planck's constant by the square of the electric charge, that has, in fact, exactly the units of resistivity or resistance in 2 dimensions. Resistivity in 2-dimensional resistance. So at ohm, this has the same units as h over e squared. So h over e squared is what, 26 kilo ohms or something. And so the resistivity or the resistance, which is roughly the same thing in 2 dimensions, of these metals is much larger than this quantum unit of resistance. Now, why is this significant? Well, if you look at other materials like aluminum, copper, gold, or whatever, and if you make it really dirty, the resistance starts going up, and it becomes a very poor conductor, a bad conductor. And at some point, when its resistance is of order, the quantum unit of resistance, h over e squared, you find that it just becomes an insulator. It just stops conducting completely. And this is universally found in all metals that have quasi-particles. So here there seems to be a resistance that's much larger than the quantum unit of resistance. And nevertheless, it's a metal. And it's a metal in the sense that the resistivity increases when you increase the temperature. If you take something like copper, which is a metal, and you increase the temperature, the resistance becomes larger because the quasi-particles have more obstacles to collide with as you raise the temperature. But if you take an insulator, like a piece of diamond, which is a completely good insulator, if you raise the temperature, the resistivity goes down because you get excitations above the insulator which can carry charge. So here the resistivity has a metallic form. It becomes larger as you increase the temperature, but the resistance is that of an insulator. So these are the bad and incoherent properties, which have been a puzzle really since 1987, and most theorists, feel quite lost as to how you're going to put all this together. Okay, so let me show you another phase diagram of a different material, which is also a high temperature superconductor. And I'll spare you all the details of all the other phases. There's a superconductor here, and there's a region here which has exactly the properties that are advertised. The resistivity is linear in temperature, and it's much greater than h over e squared. Okay, so many of us over the last 20 years have been worrying about, if I remember how to go back now. Sorry, I haven't quite got used to this thing here. How to understand this phase of matter, which is really quite ubiquitous in this class of materials which are high temperature superconductors. Okay, so we're not there yet, but I want to talk about some unexpected offshoots, I would say, of thinking about this strange metal. So it's sort of like, it's in a grandiose comparison to Fermat's last theorem. It's not really the theorem that counts, it's all the things you discover along the way. Okay, but here maybe even the theorem counts, we'll see. Okay, so what are so let me try to, so that's what I want to talk about. So now let me step back a bit and go back and talk about familiar metals in a more precise way. Right now I was just waving my hands, giving you this picture, but let's say, what do I really mean by a quasi-particle? So what I mean by quasi-particle excitation, what I mean more precisely is that if I have a piece of metal which is sitting in its lowest energy state, and then I create an excitation here, I get a lump that's moving, and I create an excitation here, I get another lump that's moving, and most of the time they're really far apart, and they move independently of each other. And so by having one excitation here and another excitation there, I can create another excitation, which is the combination of them. So I can add excitations together. So that's really, in some sense, the more formal and precise definition of what a quasi-particle is. It's an excitation of a quantum system, an infinite quantum system, which is additive, that I can combine them to create more. So for example, if I have a set of quasi-particles with energy E alpha, alpha is a label that goes from 1 to n. If I have n sites in my system, then I can get a state where either the state alpha is occupied, that will be n alpha equals 1, or it's empty, which will be n alpha equals 0. So the total number of states is 2 to the n, because these can take 2 to the n values. So I can make 2 to the n states of total energy E, and the essence is that you can get 2 to the n states, or e to the alpha n states, of the many-body system, and you can think of them as just some simple additive combinations of the quasi-particle energies. Now, every now and then the quasi-particles will come close to each other, so there will be some term that depends quadratically on when they're both present. So there will be some coefficient f alpha beta. And then even more rarely, 3 of them can come together, and there's another term there. So you just get some series which at most has polynomial in n numbers, so n squared, n cubed, or n to the 4th numbers. And from this very small set of numbers, I can create, by just taking different values of n to the alpha, 2 to the n states. So when I say it this way, this seems like ridiculous. How can you have all this, so many different possibilities for a many-body system to have excited states? E to the n, e to the 10 to the 23 is unbelievably large number. That's how many states I have to play with. But I can describe them all very accurately, at least the low energy ones, by a much smaller number of states, of order 10 to the 23, not e to the 10 to the 20. So that's much, much smaller and much more manageable. And that's what we always assume when we use the quasi-particle idea. And we seem to get away with it. Okay, except in these new materials. Right. So that's a more precise definition of what is a quasi-particle. Let me make another one, which is that if I take a metal sitting there, suppose I just kick it, I dump some energy into it, what's going to happen? Well, I dump some energy into it, so I'll create a bunch of quasi-particles. So they'll start moving around, and then eventually they'll collide with each other. And we know if you take a gas in this room and put some energy into it, eventually it becomes indistinguishable from the state before. Maybe you heated it up a little bit, but it basically reaches equilibrium. So that should also happen to any metal. If you dump some energy into it, eventually the energy will flow away and the system will reach equilibrium, perhaps at a higher temperature. So you can then ask, how long does it take for a system with quasi-particles to reach local equilibrium, I should say? Well, we just have to figure out at what rate the quasi-particles collide. Now, it turns out that this equilibration happens relatively fast. This is what Boltzmann taught us at the end of the 20th century, or 19th century, that basically in this gas, in this room, the equilibration time of this gas is basically equal to the mean collision time between two molecules. That's all you need to figure out. What is the mean collision time? So you've got to go back to this quasi-particle gas and just redo Boltzmann's calculation. How long does it take for two quasi-particles to collide? And once a couple of collisions have occurred, that's enough for the whole thing to just equilibrate locally and have some effective temperature. So if you do that very simple redo Boltzmann's calculation, in fact, the only change is you have to replace the Boltzmann distribution function by the Fermi function. That's all, near a Fermi level. So that's the only place really quantum mechanics comes in for fermions. And then you find that the time it takes to equilibrate is of this form. It's basically the Fermi energy, which I introduced earlier, divided by kBT squared. Kb is Boltzmann's constant, T is the absolute temperature, and h bar is Planck's constant. So what I want you to notice is that at low temperatures, as temperature goes to 0, this time blows up. It becomes very long. So the cooler the system is, the longer it takes to equilibrate, and it diverges as 1 over temperature squared. Just remember that. So these are two properties of systems with quasiparticles. Their energy levels are given in this polynomial type expansion, and they take a long time to equilibrate. As we'll see, this time is quite long. I haven't told you long compared to what, but it's long. I'll tell you what it's long compared to in a while. And these are the two basic properties of quasiparticles. All right, so now what I want to do is just take a very simple model. This is just for fun almost, but it's really to prepare you for the more interesting part that comes in a minute. Just imagine I have a bunch of sites in which, say, electrons can sit in some box. So this is some little finite space, and I have these sites at random positions at which electrons can sit. And I take a bunch of electrons and put them on these sites. And now I allow the electrons to move. And let's imagine actually they're free electrons. And the electrons have the ability to hop randomly from any site to any other site. So you could have that happen, this happen, and so on. So all of these, there's a random amplitude for them, any electron to hop from site I to site J. So that's it. That's the model I want to study. This is sometimes called the random matrix model because the electron is just described by a random matrix with random matrix elements from between any pair of sites. The only place the fact the electrons feel each other is from the exclusion principle. So notice no electron ever went from a filled site to a filled site. It always goes from a filled site to an empty site, like that. If you want to actually see some equations, this is how people write it in graduate school. You have this electron operator that takes you from site ij to site I. Tij is a random matrix element, random number, and you just have n squared random numbers here, and you just have to figure out what the states of this type of Hamiltonian are. So books have been written on that. A lot of things are understood. So what you know, for example, is that there are n eigenstates. So I'm sorry, the freshmen are probably lost at this point. But anyway, maybe if you've taken linear algebra, these are just the eigenenergies of that random matrix. So the n eigenenergies, which go in some window, and this is the density of states, or the density of eigenenergies at some level omega. So there's a whole bunch of discrete levels here, spacing about a 1 over n, and this is the density of them. And so this is the Fermi energy, say, and you occupy all the states below the Fermi energy. All right, so that's a really very, very simple model. Now, what I show here is another fun plot, where what I did was I took a 12 by 12 random matrix. That's really all I did. Take a 12 by 12 random matrix with 144 random numbers and diagonalize it. So I got 12 eigenvalues, which were E alpha. And then I occupied some fraction of them. I guess half of them, I believe. No, any number n. I put some arbitrary number n, right? So the number of many body states, capital E, is 2 to the 12, or 4096. Because the n alpha can either be 0 and 1, and there's 12 of them. So there's 2 to the 12 many body states. Whereas the number of random eigenvalues is just 12, epsilon. So from these 12 random numbers, I create 2 to the 12 numbers, E. And I just plotted all the 2 to the 12 right here. Okay? So this is like the many body eigenstates, eigenenergies. So the total number of states in this region, the width of this region is about an n, so 12. The total number of states is 2 to the n. So the mean spacing between levels would be 2 to the minus n. Very, very tiny. N is only 12, but imagine n is 1,000, then you couldn't even plot it. And it's not that hard to take n equals 1,000 in this calculation. It's a 1,000 by 1,000 matrix. Even my iPhone can diagonalize that. No? Yes, it can. Okay. All right. So I've only done 12. So there's a very tiny spacing here. But if I look at the bottom, something funny is happening. The spacing seems much larger. Why is that? Well, so why is this? First, you ask, why is the spacing so small here? what happens between one level and the one just above it? What's happening? Well, I only have 12 random numbers, and their spacing is 1 over 12. So they're really quite far spaced, not this close. So what happens between one level and the next is that the n alpha, so that's some sequence of zeros and 1. So if I have one level, I have one sequence of zeros and 1. And I have the next level is another sequence of 0 and 1. So it must be the case that the sequences are completely different. You go from one level to the next, you get an entirely different sequence. And so you can, by accident, get a number that's very, very close to the previous number by taking a different combination of 12 random numbers. However, what's happening at the bottom? What's happening at the bottom is something very different. So now you have these, so I now actually show the 1 over n spacing level. So these are spaced by 1 over 12. Of course, 12 is not 12 in this case. And all the states below the green line are occupied, and the ones that are empty. So the ground state is where n is equal to 1 for all of these states below the green line, and n is equal to 0 for all the states above the green line. So how do I keep the first excited state? The first excited state is I take the highest occupied orbital and move it to the lowest unoccupied orbital. Homo-LUMO transition in chemistry. And that spacing must be 1 over n, because the spacing between individual levels is 1 over n. So you find this very important feature that the spacing down here is much, much larger, exponentially larger than the spacing in the typical point of the spectrum. And that is, again, a consequence of having quasi-particles. I mean, this is a bunch of free electrons. The energy is explicitly of this form, so that nobody had doubted they are quasi-particles. But I'm just illustrating it by just drawing these energy levels. All right, so now let me turn to the model that people now call the SYK model. So this is something I proposed, some variant of it I was proposed by my graduate student, my first graduate student, Jinwoo Ye at Yale 25 years ago. And Kitev recently improved it and had some very deep insights about its properties, which I'll mention a bit later. So now people are calling the SYK model, and I'm certainly okay with that. Okay. So the rest of my talk will be largely about the SYK model. This turns out, to be a model of a strange metal. That's what we were trying to do. But as we'll see, it's also a model of a black hole, believe it or not. Okay. So again, I take the same set of sites, and I put some electrons in them. And now I allow the electrons to move, but I put one very important restriction. The electrons can only move in pairs. That's it. Not one by one, but only in pairs. So for example, I can have those pairs move there. Think of that as a quantum mechanical tunneling event. You're going from 2 electrons here to 2 electrons there. And there's some amplitude for that. There's some quantum mechanical tunneling amplitude. And that amplitude I don't know, so I'll just say it's a random number. That's it. Okay, so that's another random process. So these are all, so any pair can go to any pair of electrons can go to any pair of unoccupied sites with a random amplitude. That's the model. That's it. And so what's happening is, since the electrons can only move together, this model, unlike the previous one, has the feature of entanglement. Every time an electron moves together, it's entangled with the other one, because their positions are quantum mechanically linked forever at that point. So each electron is basically entangling with every other electron when it pairs with it. So they're all entangled with each other, and this is, in some sense, a model which has nothing but entanglement. That's all it's trying to do, is maximize entanglement between the electrons. Yeah, there we go. So that's the model, and this turns out, as I've said, both a strange metal and a black hole. So again, if you want to see some equations, this is the model. The electron can go from site L to site K, site K and L to site I and J with an amplitude Uijkl, and all the Uijkl are random, independent random numbers. That's it. And okay, so now we can go ahead and try to solve this. So what we showed already in 93 was this model is actually exactly solvable in the n goes to infinity limit. If this number of electrons is large enough, then we can solve the whole thing. But we only solved a few things, and people are still solving other things, and the black hole connection emerged slowly over the years. I should also mention that way before us, even in the 1980s or 70s, nuclear physicists studied the same model, which they call the two-body random ensemble, as some kind of model of what's happening in a complex nucleus. So there you think of this whole cluster as one big nucleus, and the pairwise motion has to do with different neutrons and protons inside the nucleus. So they did some numerical simulation, but they didn't solve it and didn't figure out anything that I'm going to say from now on. But they did look at it. But anyway, something I only found out recently. I gave a colloquium, and the nuclear physicist told me, wait a minute, we had already looked at this. Anyway, okay, so now let me just do exactly what I did for the first problem. Let me take 12 sites and just diagonalize it. Now here, I couldn't possibly take 1,000 sites, because the total number of states is 2 to 1,000. And let alone my iPhone, even the most powerful computer in the world couldn't do it to take 1,000 sites. But 12, yeah, okay, you can do. So here, for 12 sites, previously I had to diagonalize a 12 by 12 matrix. Here, for 12 sites, I have to diagonalize a 4096 by 4096 matrix, which is barely doable by my iPhone. But that grows exponentially fast. You go from even 12 to 20, you're already talking about using a supercomputer. So people can do about 20, or up to 30 today, I think. All right, so this is the same set of levels by diagonalizing for 12 sites. Now diagonalizing a 4096 by 4096 matrix. Again, for exactly the same reasons, the mean level spacing is 2 to the minus n. Okay. So then, just like I did before, let's look at the bottom of the spectrum. Well, the picture is not very good. But what we showed in this paper with my friends from Paris, George and Parcolet, that the spacing here is not 1 over n, but it's still much smaller than this. This is e to the minus n log 2 here. And it's here e to the minus s naught. And this number s naught, we computed in 2001. I'm really proud of it, so I'm showing you exactly what it is. And this number s naught will, although we didn't realize it then, will be connected to the entropy of a black hole. Anyway, but for now, all you need to know is that s naught is less than log 2. Which means that the spacing here is much larger than the spacing in the middle, because e to the minus n log 2 is much, much smaller than e to the minus any number smaller than log 2. It's up in the exponent. But it's not exponentially larger as 1 over n was, okay? So the fact that this is still exponentially small, but much, much larger than that, but still exponentially small, means that I can possibly describe these levels by polynomial numbers. I can't. There's just so many of them. We don't even know where they are. And they're all different. And so there's a huge amount of quantum information that's contained in these low-lying levels. So we know that you can't do that. And this is really the first model where you can really show this in so much detail. There's just no way this model has a quasi-particle, because we proved in 2001 that the level spacing here is exponentially small. So there's no way that I can take polynomial n numbers and describe all the levels here. Of course, n is 12, so you can't really tell the difference. But I could have made this plot for n equals 25, but then there'll be so many levels that we just black. Even with the thickness of then you're talking about millions and millions of levels, and I can't plot them. So people have done that sort of numerics, including my student Wenbo Fu. We ran through this carefully and numerically checked that this is indeed true. Okay, so that's the basic property of the SYK model. Hopefully it's clear what it is. It's just this pairwise random motion of electrons, or any fermion, on a finite cluster. And it has the property, because of these level spacing, there's one way to see it, that there are no quasi-particles. Okay, and so I've given you an example of a state of matter, ridiculously simple as it may be, or artificial as it may seem. but at least it's a proof of existence. There are states of matter where there are no quasiparticles. So any questions so far? Hopefully everyone's with me, because things are now going to get a little technical. Yes?
I do have a question. And you intrigued me when you said that you view the hopping of this pair of electrons in terms of pair and entangled pair.
Yeah.
Where do you see the entanglement? Where do you put the information about the state of this electron? It doesn't come.
Well, I mean, that's the Hamiltonian. I'm just talking about the low energy state of this Hamiltonian.
Right.
And maybe I'm just saying that if I try to do some perturbation theory, I start from some initial state and I hit the Hamiltonian on that state, I will always create EPR pairs of electrons every time I hit the Hamiltonian. Because there's a state I start with, which is 2 electrons here, and the state I end with, where they're over there. I can also come back, and so I'm thinking of time evolving as some kind of hitting the Hamiltonian many times. And each time I do this, I entangle 2 electrons. Because electron is, each electron has to pick one of the other electrons. It will pick different ones at different steps. And so one step it will entangle with this one, the other step will entangle the other one. We don't have very good measures of multi-particle entanglement. I mean, as I'm sure you know. For 2-particle entanglement, there's all kinds of measures, and entanglement entropy is a rather crude measure for multi-particle entanglement. But here we're not trying to come up with a classification of different types of entanglement. It seems like an impossibly difficult task when you're talking about millions of particles. We're just looking for different states of reasonable local Hamiltonian. That's all. Our 2-body Hamiltonian in this case. Yes?
When you write that U, I, J, K, L are independent random variables, you take an expectation value, it gives 0. So in what sense do you take this expectation value? Meaning, like, one is, what does repetition say of
excellent question. So, right. So this is a model when n is large enough, which is self-averaging. That is, what you have to do is you have some random number generator, and say I have 12 sites. So I need 12 to the 4 random numbers. So you toss the coin, get 12 to the 4 random numbers, and you get one model. And then you go ahead and solve it and look at its properties. And I'm talking about its properties. And for certain properties like the entropy density or the local Green's functions, one sample is enough. Okay, I don't have to average over ensembles. So that's true, for example, the gas in this room. I mean, I only have one sample, but I know it obeys PV equals nRT. And the way I prove it is by averaging over the Boltzmann ensemble. But I don't really need to average. It's just a very convenient way of doing the calculation. Because it's something like the central limit theorem. One sample big enough is enough to get self-averaging property. Now, it turns out here that is the case. That wasn't clear when we solved it in '93. We were actually very worried about this issue. But we kind of guessed it's going to work. It's only recently through the improvements of Kitaev that we're able to numerically check that that's actually true. So this calculation I just mentioned of S0, that we computed it a while back, but it's only when we're able to numerically check it in a paper, this, and there were other papers by others too, that this works. And then we were starting to feel confident that the assumption of self-averaging, which was built into our calculation, was actually correct. Okay, so that's an excellent question. It's behind many years of headache and worry, but it's all okay now. Yeah.
If you hybridize this, the SYK model with the first model that you talked about, allowing for single jumps.
Just hold on. That's where we are coming. I'm coming exactly to that. Great question. Okay. Anything else? All right, so I'm going to flash a few results from the last couple of years of various things that have been learned, and I will not really have much time to go through all the technicalities. So, for example, I told you that the low energy density of states was e to the n s naught, as we numerically checked. So what's the subleading correction to that? That's been worked out by these 3 people, and everyone here is in fact a string theorist. So there is some connection to string theory and quantum gravity that was required to work this out. And it also works numerically and so on. But I'll give you an inkling of where that's coming from in a few minutes. But it is simply just a correction to the density of states. The subleading term is that, and then there's a correction which goes as e to the root n. So once you have the density of states, you can compute the entropy. So another way to say this is this particular entropy. The entropy increases linear with temperature. That was also first obtained by a bunch of string theorists. The first term was by us, condensed matter physicists. The next term was obtained by string theorists. Okay, so this was already obtained in our very first paper. The Green's function. So this is some kind of amplitude for an electron to retain coherence at one point, or just remember that it was there. This decays as 1 over square root of tau, and the fact that it's a fractional power was another indication, and was clear to us then that there are no quasi-particles here. So this is why this model is incoherent. This is a technical term, not to say that it doesn't make any sense. It's just incoherent. So this is definitely technical, and I apologize, but anyway, so my friends in Paris, Antoine Georges and Olivier Parcolet, they were the only other people interested in this for that decade, figured out that the finite temperature generalization of 1 over square root of tau was temperature over sine t tau. So if I send temperature to 0, this basically becomes 1 over square root of tau. This t will cancel the t in the sine. You just do the sine x equals x small x expansion. So, all right, so there's some high school physics. But this function, to people in the know, people who study what are called conformal field theories, is very significant, because it was certainly a sign that there was some hidden symmetry in the study of this model. So hidden symmetry called conformal invariance. And we certainly, when I saw this, I kind of felt that was the case. I should have dropped everything and really tried to work on this, but nobody else was paying attention, so I also kind of lost interest. But this was one of those bellwether signs that was kind of ignored for many years. More recently, we have come back to this point, and also looking at this, how things depend on temperature, we can figure out that, and we have studied this more carefully with my group, that this equilibration time, remember I showed you this equilibration time for a system with quasi-particles by just doing this Boltzmann calculation. It went as 1 over temperature squared. If you do that calculation here, you find it goes as 1 over temperature, not 1 over temperature squared. But what's also very interesting, there's nothing else. These are just fundamental constants of nature. Planck's constant. Kb is just not really, it's a fake constant. It's just, if we should measure temperature units of energy, then you wouldn't need Kb. Okay. So, and temperature measured in absolute units. So there's no U, there's no chemical potential, no Fermi energy, nothing. Just temperature. So this is kind of surprising, and well, this is something that when we saw the results, we also took note of. This seems to be equilibrating. First of all, it equilibrates much faster at low temperature. So this time is much smaller than 1 over temperature squared as temperature goes to 0. So it seems to equilibrate very fast. Okay, so now let me make some very general statement. Having this example under our belt, let's try to generalize fearlessly. Historically, things went in a different order, but anyway. So how do I talk about systems? Now that we have an example of a system without quasi-particles, what does this teach us in generality for other systems? This is, after all, an artificial-looking system, which you just happen to know how to solve. Well, first of all, this is definitely not true, that the energy is some polynomial of single particle properties. Okay, this is like defining something by what it's not. Never really a good idea. But anyway, it's a start. It's not this. Okay, so how do we take a more positive point of view? Well, maybe this is very general, that this equilibration time is some number, like pi or something, times Planck's constant divided by temperature. Maybe that's kind of a super universal property of system without quasi-particles. And this was something I conjectured about, I don't know, 20 years ago, that that's the case. Moreover, what we notice is this time is much, much shorter. It's very quick than the time for a system with quasi-particles. So maybe if in any system there's kind of an inequality that any quantum system, if you ask how long it takes to equilibrate, it always takes longer than this very fundamental time, Planck's constant divided by temperature. So it's sort of like an energy time uncertainty principle, which is that there's just no way in any system that no matter what you do with all the couplings and the energies in it, that it can equilibrate faster than this time, h bar over kT. Okay, so this was a conjecture I threw out in the preface to my book, just as a side thought, and it may turn out to be the most interesting statement in my book 20 years later. Luckily, I put it in there. It wasn't even there in the first draft. So, first of all, is this bound true? Well, everything we've talked about so far, it works. So, in a Fermi liquid, is 1 over temperature squared. This is it's obeyed. But you can say, okay, so I haven't told you what this constant C is. Even without knowing what it is, we can't have any system in which the equilibration time goes as, say, 1 over square root of temperature. And no such system is known. You can now open all the textbooks and look at all the papers in Physical Review B and see if you can find such a system. No one's ever found such a system. Closed system that equilibrates in this time. Another interesting thing to notice, and this gives some insights to where this is coming from, is if I do classical mechanics, Newtonian mechanics, which means h bar goes to 0, this is kind of an empty statement. And this tau equilibration is greater than 0. Well, of course. But so that means that, for example, I have a bunch of springs. You know, you've seen these things with springs all coupled to each other. Not in a line, but in some complicated way. If you just push them, eventually they'll spring around and they'll start becoming indistinguishable from a thermal state, or the gas in this room, for example. So let's take the example of the gas in the room. The molecules are zipping around, they collide, and it becomes like PV equals nRT, it becomes equilibrium. So let me make the molecules even lighter, make them very, very light and move them really fast. They'll come to equilibration even faster. Make the collision cross-section really large, make them big. So in a classical model, just by scaling up the frequencies of the springs, or just changing the parameters of your particles and how fast they move, you can make them equilibrate as fast as you want. That's kind of obvious. It's true. But in quantum mechanics, you can't do it. And the reason is the following. Quantum mechanics is discrete. There are energy gaps. So if you make some coupling very large, what it does, it doesn't make the system move fast. It just makes some energy levels really far from each other. And then that's no good for equilibration, because you only want to use the low energy states. So you really need lots of low energy states, like we found in the SYK model. Lots of them to equilibrate fast. And once you have quasi-particles, there's fewer states around, and equilibration is longer. So that's kind of the rationale between below this bound. Okay. How am I doing on time?
10 minutes roughly.
10 minutes. Okay, I haven't even started on black holes. Okay.
15.
All right, but I do want to talk about mixing together one body and two body hopping. And connect up with the beginning of my talk, and I'll just say a few things about black holes. So here's a model that was studied by this group at Santa Barbara. Song et al. Song is now a student at Harvard, and Leon Valence is the senior author. So here you take a lattice of SYK models. So you take each one of these dots is what I've been talking about so far. So electrons can move in pairs on that dot. That's this term in the Hamiltonian. But I also allow electrons to hop from one dot to the next. That's this term. So it's a mixture of the two models, where within each dot it's like the second model, and between the dot it's like the first model. Okay, so this is another model that you can solve. But now this has a notion of space. It's living in a plane. And so Song et al. Computed the resistance. You can solve it and compute the resistance. And lo and behold, you get this wide energy regime below this small energy scale called the coherence scale. So above this, temperatures above this scale EC, which is 1 down here, it's incoherent. And in this incoherent regime, the resistance is linear in temperature, T over EC. Now T is bigger than EC in this regime here, times H over E squared, so the resistance is much bigger than H over E squared. So here's a model, and really it's the first model, I think, which is strange, incoherent, and bad. So it has a very large resistance, it's a linear resistivity, and it's strange because, well, there are no quasi-particles. So this is very exciting because we now think that this is, this kind of criticality of the SYK model may really be behind quite universally, as ridiculously contrived as the model seems. It's a great starting point for similar physics in a wide class of models. There's many more papers I know that are coming out which have been exploring how this very simple physics I've described actually may not be may actually be quite a good starting point to understand real metals, strange metals. Okay.
Wait, I'm really confused.
Yes. I went through that quickly.
Electron move between the SYK models?
Sorry?
What happens to the partner of the pair? Like,
you don't care. Any one of them can hop from one dot to the next.
Right. So the pair, the partner of the pair that stays in the same.
There is no partner. So in this thing, electron L can partner with electron K to go to side J and I, but it's completely polygamous. Each electron will partner with every other electron, even within a given dot.
Okay.
They're not pairing up. They're just for one instant they find a partner and then they find another partner. Okay. And then any one of them can hop from here to there. Okay. So that's the model. I mean, looks contrived, but it's a beautiful idea by Song et al., which seems to have been the start of much work even in the past year of getting closer to a theory of realistic strange metals. Okay, I'm almost out of time, so let me just say a few words about black holes. So why could any of this have anything to do with black holes? Sounds insane. Okay, but I'll just try to at least rationalize some of it. So black holes were objects that were discovered in Einstein's theory of relativity, first by Schwarzschild. Soon after, Einstein wrote down his equation for general relativity. For the longest time, people thought they were just an artifact, but I think starting in the 50s, people started taking them seriously. And eventually now, of course, we have many, many astrophysical examples of real black holes, including the ones observed so beautifully in LIGO. And in the mid-70s, Bekenstein and then Hawking started thinking seriously about what is the effect of quantum mechanics on a black hole. And they came up with some rather remarkable conclusions. One is that in Einstein's theory, a black hole is literally what the name says. It's a bunch of matter which basically is trapped inside the horizon, and it's completely featureless. From the outside, it looks like all you need to know is the mass, and it's a state which is essentially completely at rest. It has no energy, no kinetic energy as such. It's just sitting there. It's essentially at absolute zero. And what Hawking said that once you include quantum mechanics, black holes are not at absolute zero. They're at some temperature, which we call the Hawking temperature. And moreover, it's seething with lots of fluctuation. It has a lot of entropy. It has lots of degrees of freedom that you wouldn't see in Einstein's theory. Now, I don't have time to go through the reasoning behind this, but that's okay. Let's just take that as a brilliant insight by Bekenstein and Hawking. Another of their insights was even more astonishing. The entropy of a black hole is proportional to its surface area. Normally, take any system, its entropy is proportional to volume. That's the number of degrees of freedom in it. But here is this huge object, very dense object though, and when you apply quantum mechanics, it seems to have quantum degrees of freedom which essentially only live on its surface. Okay, so these were remarkable observations, and by Hawking and Bekenstein in the 70s, and really for the longest time they just stood there because nobody knew what to make of them. But they've really become the center of theoretical physics in the last 15, 20 years. So what is, from my point of view, the fundamental reason for this? Well, let me just show you here the famous first LIGO collision between black holes. None of this has to do with quantum mechanics or anything I have to talk about. But I just want to illustrate this very last stage of the black hole becoming a perfect sphere. And after this point, the black hole is a featureless sphere in Einstein's theory. And as far as LIGO is concerned, that's correct. But we can now ask, but Hawking told us this featureless sphere is a system in thermal equilibrium at some temperature. So we can ask the question, how long does it take for the black hole to settle down from some oscillating shape, this very, very, very last stage of the cooling down, to something that's in thermal equilibrium? How long does it take? Well, you can open up your general relativity book and work it out in Einstein's theory. How long does this ring down of the ring down phase last? And Einstein's equations of general relativity tell you that the time is 8 pi gm over c cubed, where g is Newton's gravitational constant, m is the mass of the black hole. And for 60 solar masses in this black hole, that's 8 milliseconds. Now, I remember I told you that Hawking said, no, black holes are actually quantum objects and they have a temperature. All right, so if I just open up Hawking's paper and look up his temperature that he computed, and I compute this minimum possible time for a quantum system to equilibrate, which is h bar divided by now Hawking's temperature. That turns out to be equal to what you get out of Einstein's theory of relativity. So that's a totally amazing fact, and that's the key equation behind the connection between black holes and strange metals, or systems without quasi-particles. Both black holes, when viewed as quantum objects, and strange metals are champions in thermalizing. They thermalize as fast as possible. And they have this same time, h bar over Hawking's temperature. All right.
Wait.
Yes.
Then I suggest we let
At
you
the end.
finish.
Okay.
No, go ahead. Sorry.
No, just the Hawking temperature.
I'm pretty much done, but I got to get used to this silly thing.
The Hawking temperature is proportional to the surface area, proportional to the mass squared. Then, so.
No, the entropy is proportional to surface area.
Entropy. I'm sorry.
Or the
Yeah,
temperature.
never mind
I hope I've not made I think that's correct, but I may have there might be a typo there. I had to look it up. I don't remember this part off the top of my head. Anyway, just so then you have this feature that this fundamental time is again making a reappearance. Okay, so let me just skip ahead and show you one picture. So imagine, that I have some space-time. So here's my physical world on which my SYK dot is sitting. That's where I am. I'm a little ant. These electrons are moving in 2 dimensions on this little dot. So that's my quantum theory. At the same time, I have a theory of a black hole. And the black hole lives in this space where it has an extra spatial dimension. And here's the black hole. So the black hole lives, if this space is 2-dimensional, the black hole lives in 3 dimensions because it has 2 dimensions in this direction and this 3rd dimension. And this is the horizon of the black hole. The black hole is really behind it. And this space is curved, this extra dimension. So now the claim is that the theory of quantum gravity in this very special space, so the theory of quantum gravity in this very special space, which is called anti-de Sitter space, is in fact the same, the dual of the quantum theory I've just described. So what does it mean? It means that, first of all, the entropy of the black hole is equal to the entropy of the SYK model. And now we can understand another thing, this holographic principle as it's called. Why does the entropy depend on the area? Well, if you believe this claim that this 3-dimensional quantum gravity is the same as a 2-dimensional quantum system, and its entropy is the same as that, well, the entropy of the black hole is the entropy of this, and the entropy of this is proportional to its area, it's proportional to the number of sites have this two-dimensional structure. So they are done. Because so that's why you see why you have this, it's crucial to have this dimensional reduction. A black hole in 3 dimensions looks like a quantum system in 2 dimensions. And the simplest type of black hole that's been known in Einstein's theory, this 2-dimensional black hole in anti-de Sitter space, turns out to be precisely equal in its low energy properties to this model. So these things that I showed you here before, this factor of cinch actually came from starting from the black hole, and it's also been computed starting from the SYK model, and you get exactly the same number, and so on. All right. So I'm going to conclude then. Yeah, so these are the bullet points. I really didn't get time to explain the last one. A system without quasi-particles are one which, well, you can't rewrite the energy levels in terms of simple one-particle type excitations. And these are systems which are champions in thermalizing and become chaotic in a time of order h bar divided by temperature. And these turn out to be also universal characteristics of black holes in quantum gravity. Thank you.